I'm Arjita Kulshreshtha, a fourth-year graduate student in Professor R.T. Jayaraman's group at the University of Delaware, and I will be sharing with you my work on the effect of attractive graph matrix interactions on the dispersion and aggregation of polymer grafted particles in polymer nanocomposites using theory and simulation. Before I begin, I wanted to give a brief overview of my work, which involves theory and simulation studies of structure and thermodynamics in polymer blends and polymer nanocomposites. Some of my work was focused on understanding the impact of directional and isotropic graph matrix interactions on grafted layer wetting in polymer nanocomposites. This was done by the development of a coarse-grained model for directional interactions that captures the long length and time scales of polymers, as well as the short length and time scales of hydrogen bond formation between graft and matrix polymers in polymer nanocomposites. We're also using this coarse-grained model to understand how hydrogen bonding interactions promote formation of disordered microphases on increasing the strength of hydrogen bonds in immiscible polymer blends. Further, we're also working on tuning this generic coarse-grained model to capture hydrogen bonding effects on structure in specific polymer chemistries, namely poly-4-vinylphenol and poly-2-vinylpyridine. So all of this work is focused on understanding the impact of directional interactions on structure in polymer nanocomposites and polymer blends. And what I'm going to be talking to you about today is cohesively tied to this, that is, the impact of attractive graft matrix interactions on the size and hardness of polymer grafted particles and its implications on structure in polymer nanocomposites. So just a brief background of what has already been done. In polymer nanocomposites with polymer grafted particles, the dispersion and aggregation of grafted particles in polymer matrix is linked to the interpenetration between graft and matrix polymers and the design parameters that increase grafted layer wetting drive particle dispersion. So in nanocomposites, when the graft and matrix polymer chemistry is the same and the grafting density is high, wetting dewetting is purely entropically driven. And at this entropic limit, previous studies have established the design rules for increased grafted layer wetting. And these include increasing the length of graft chains compared to the length of matrix chains, increasing the stiffness of matrix and graft chains, increasing the polydispersity of graft chains, and increasing particle curvature. On the other hand, when the graft and matrix polymer chemistries are dissimilar and attractive, wetting dewetting is driven by a combination of entropic and enthalpic driving forces. And for these nanocomposites with attractive graft matrix chemistries, a previous study in our group looked at how wetting or interpenetration between graft and matrix polymers is linked to the dispersion and aggregation of grafted particles in polymer matrix. And they found that wetting dewetting and dispersion aggregation occur as distinct transitions. The wetting transition, quantified by the wet monomer fraction, is a continuous transition, while the dispersion aggregation transition is a sharp first-order transition on increasing temperature. They also found that the more wet states were found to be more dispersed, while the less wet states were found to be more aggregated. And at each grafted filler fraction, the dispersion to aggregation transition occurred when the wet monomer fraction was equal to that in analogous athermal or purely entropic graft matrix PNCs. So while this work focused on certain strengths of attractive graft matrix interactions, the question that we're after is, how does increasing graft matrix attraction strength affect grafted layer wetting and particle dispersion? So focusing on the left-hand side of this plot and looking at strengths of graft matrix attraction, which are higher than those explored in this previous work, and seeing how that affects the structure in polymer nanocomposites. And to do this computationally, we use a coarse-grained model where the nanoparticle is modeled as a sphere of diameter dp. The nanoparticle sphere is surrounded by surface grafting sites that act as tethering points for the graft polymer. And the number of these surface grafting sites is fixed by the grafting density, and the length of graft and matrix polymers is also fixed. Our coarse-grained beads interact through non-bonded interactions. So to simulate attractive graft matrix interaction, we use the Lennard-Jones potential, where we fix the strength of matrix-matrix and graft-graft interaction at 0.1 kT, and increase the strength of graph matrix interaction from zero point 0.1 to zero point 0.2 and zero point 0.3 kT to model progressively attractive graph matrix interactions. So with the co-strain model, as shown in the previous slide, we perform molecular dynamic simulations using LAMMPS package in the NBT ensemble. For all simulations, we keep the box volume packing fraction at 0.37 to simulate melt-like conditions. And we simulate various polymer grafted particle filler fractions, which is defined as the volume of the graft polymer and particle beads relative to other beads in the simulation box. So we simulate single particle PNCs at a low phi PGP, as shown here. So you can see the particle and the graft polymer in blue, and the matrix chains are seen in green. We also simulate multiple particles at a higher grafted filler fraction, and the various components of this PNC can be seen here. The second box here shows the particle with the graft polymer, and the matrix chains are hidden, while the third box just shows the particles. That said, using MD simulations to simulate multiple particles tends to be computationally intensive, and there's a high propensity for these simulations to get kinetically trapped, and therefore we use theory to confirm and complement our MD simulation results. So we use the PRISM, or the Polymer Reference Interaction Site Model theory, wherein each component of the nanocomposite is treated as an interaction site. So we have three types of interaction sites: the particle, graft, and matrix. And it involves the solution of a generalized Ornstein-Zernike-like equation that relates the intermolecular pair correlation to direct pair correlation and intramolecular pair correlation. Intramolecular pair correlation is calculated from single particle MD simulations. And for direct pair correlation, we use closure equations, and based on extensive past experience with similar systems, for the particle-particle pair, we use the hypernetted chain closure. And for all other pairs, we use the Perkasiewicz closure. And the PRISM equation is then numerically solved using the pi-PRISM package to obtain spatial correlations, which include HFK, which is related to pair correlation functions, and also structure factor. So first, let us consider the wetting and dispersion behavior for purely entropic PNCs. These correspond to PNCs in which the graft and matrix polymer chemistries are identical, and they are modeled by keeping the strength of graft-matrix interaction at 0.1 kT equal to graft-graft and matrix-matrix interaction. We quantify wetting by plotting the monomer concentration as a function of distance from the particle surface, and we find that the concentration of graft monomers decreases while that of matrix monomers increases away from the particle surface as expected. For information on structure within the nanocomposite, we plot the particle-particle pair correlation function from both MD simulation and PRISM theory. The peak position in particle-particle pair correlation gives the interparticle separation distance, while the peak height gives the probability of this separation. And although PRISM theory and MD simulations are two different computational methods, we find that the GPP of R from PRISM theory agrees with that from MD simulations. Then, as we increase the strength of graph matrix interaction by increasing the value of epsilon GM from 0.1 to 0.2 and 0.3 kT, we find that grafted layer wetting increases. And this is seen by the greater interpenetration of graft and matrix polymers for these cases compared to the black purely entropic case in the monomer concentration profile. But surprisingly, we find that the particle correlation also increases. And this is seen in GPP of R, where the peak shifts to largest particle separation distances, but also grows in height. And similar results are also seen from PRISM theory. To gain insight into dispersion and aggregation of particles, we plot the polymer nanocomposite structure factors, and we find that at high strengths of graph matrix attraction, the particle-particle structure factor shows reduced tendency for macrophase separation. And this is seen by the lowering in values of SPP at K tending to 0. Further, we find that the graft-graft and matrix-matrix structure factors show correlation peaks at intermediate K stars, with the R stars as shown, suggesting an ordered structure within the nanocomposite. We also recall from the previous slide that these PNCs at high strengths of graph matrix attraction also had higher wetting. Further, we find that the brush height increases as the strength of graft matrix attraction epsilon gm increases, which suggests that these PNCs have a larger grafted layer. Similarly, the number of wet matrix beads per particles also increases as the strength of graft matrix attraction increases, which suggests that more matrix beads interpenetrate the grafted layer. And due to the combined effects of having a larger grafted layer and having more matrix beads interpenetrate the grafted layer, we find that the effective grafted filler fraction increases in these PNCs with high strengths of graft matrix attraction. Thus, the reason for increased particle correlation at strong graft matrix attraction can be attributed to either high effective filler fraction or more matrix beads interpenetrating the grafted layer in these PNCs with high strengths of graft matrix attraction. And to decouple these two effects, we used prism theory to calculate the particle-particle potential of mean force at infinitely dilute 5 pgp. And these corresponds to a very low 5 pgp where effects due to a high grafted filler fraction should be negligible. And the particle-particle potential of mean force gives effective interparticle interactions. So for the black purely entropic case at a strength of graft matrix attraction equal to 0.1 kT, we find that there exists a large negative PMF well depth, which suggests that there's an increased tendency for interparticle attraction at this strength of graft matrix interaction. Then as epsilon gm increases to 0.2 kT, we find that the PMF well shifts to larger separation distances. And this is in accordance with the fact that the size of grafted layer increases as the strength of graft matrix attraction increases. We also find that the well depth in PMF reduces, and this is due to the added enthalpic driving forces at this high strength of graft matrix attraction. Then, as we further increase epsilon gm to 0.3 kT, we find that the well depth of PMF increases, which suggests that there is an increased tendency for particle-particle attraction at this high strength of graft matrix attraction. And the presence of interparticle attraction, even at a low grafted filler fraction, suggests that the correlated particle structure is not solely due to concentration effects and is likely caused by the increase in size and hardening of grafted layer. And to test this hypothesis, we performed simulations of large and hard versus small and soft grafted particles in polymer matrix. For this, the entire polymer grafted particle, along with wet or interpenetrated matrix beads, are modeled as a sphere whose size corresponds to the interparticle separation distance in GPP of R for PNCs with an epsilon gm equal to 0.2 kT and PNCs with an epsilon gm equal to 0.3 kT as shown here. The grafted particles for the case of PNCs with an epsilon gm equal to 0.2 kT are expected to be less wet and soft, and hence the particles for this case are modeled as a soft sphere, while the grafted particles in the case of PNCs with an epsilon gm equal to 0.3 kT are expected to be more wet and hard, and thus the particles corresponding to this case are modeled as a hard sphere. And the entire matrix polymer chain is also modeled as a coarse grain bead. And then we scale the relative sizes of the particles and the matrix and perform simulations of hard and soft spheres in polymer matrix at filler fractions corresponding to effective filler fractions in simulations of PNCs with an epsilon gm equal to 0.2 kT and PNCs with an epsilon gm equal to 0.3 kT as shown here. And this plot shows the particle-particle interaction, which is kept as soft for the case corresponding to PNCs at an epsilon gm equal to 0.2 kT, and the particle-particle interaction is modeled as hard for the case corresponding to PNCs with an epsilon gm equal to 0.3 kT. And our results show that having larger and harder particles at a high grafted filler fraction show a more correlated structure compared to smaller and softer particles at a low filler fraction. Further, we also confirm that larger and harder particles have a more correlated structure compared to smaller and softer particles, even when the two are at the same filler fraction, as seen for the case of 5 pgp equal to 0.307 here. Thus, increased correlation in particle positions at strong graft matrix attraction is due to ordering of larger and harder grafted particles. In other words, strong graft matrix attraction caused increased wetting, which led to larger and harder grafted particles. So to summarize, we saw that increasing graft matrix attraction or choosing polymer chemistries such that the graft and matrix interactions are highly favorable causes increased wetting, but also more correlation in grafted particle structure. And the reason for this increased correlation in particle structure is due to the increase in effective size and hardening of grafted particles with increasing graft matrix attraction. So with that, I'd like to acknowledge my funding and computing support, and I'm looking forward to taking your questions in the live session.